All right, hi guys. So we're continuing with the proof of this theorem that any finite CW complex is Hausdorff. So let me briefly remind you where we got up to at the end of last lecture. So, well, any CW complex has this kind of construction in a finite number of steps, starting with a finite and discrete space, which is Hausdorff. So let our inductive hypothesis be that xi minus 1 is Hausdorff. Then we're trying to prove that xi is Hausdorff. Xi is obtained from xi minus 1 by attaching some finite number of disks along some circles. The circles are embedded into the previous stage of the construction by this continuous map F, the attaching map. Okay, so xi is by definition this quotient of this disjoint union. And we explicitly described last time what the pairs in that relation are. There they are. We proved that the image of all those circles under the attaching map, that's this union, alpha indexes the circles that are being mapped in by F. We proved that's closed in xi minus 1. We proved that the map from xi minus 1 to xi, the right-hand map, the map that's on the board over there, is injective, and that when restricted to the complement of those attaching sites, that's what I mean when I say attaching site, this set, that is an open map. It sends open sets to open sets. And also if I restrict the, if you like, that bottom map, which sends the disks into what they end up being in the final construction, if I restrict that to the open part of the disk, which is BI, that's the interior, that is also injective and open. All right, so we proved those three things, and then we ended up by arguing for the easy case of the Hausdorff condition. Right, which was that if x and y both lie in the image of one of the injective open maps in 2, 3, well, then the Hausdorff condition holds. So then there are disjoint open neighborhoods of xy in xi. I should say distinct. Okay, so that's what we got up to last lecture. So now we've got to handle the case where at least one of them does not lie in the image of those maps. That is to say, it lies in the union that you see in condition 1 there. At least one of them, maybe both. Okay, so before I continue, are there any questions about where we're up to right now? Okay. Okay, so let's suppose one of them lies in the image of F, and it might as well be X. So suppose that X lies in, well, let's say, pick an alpha which it lies in the image of. I mean, it could lie in the image of multiple, I mean, F restricted to multiple of the alphas. F restricted to multiple of the Si minus 1 alphas, right? So here's X.
Sorry, what are we proving right now?
So we've got 2 points, X and Y, distinct. Yeah, so that's a fair question. Let's set this up more explicitly. So given X not equal to Y in Xi, so we're trying to prove Xy is Hausdorff. We suppose given 2 distinct points, and I need to produce 2 disjoint open neighborhoods of those points in order to prove that Xi minus 1 is Hausdorff. We've dealt with one of the cases, well, you know, dividing it into this easy case and then the rest. So now we have to prove that if one of them at least lies in the image, then we can still find a disjoint open neighborhoods. Okay, so let's suppose it's X. Now, So I want to give this say rho. So rho is the quotient map. Okay, rho inverse of the point x, that's a subset of the disjoint union. So it contains points that live also in the disk, potentially. But it contains a unique point which lies in the xi minus 1. Okay. Well, why is that? Again, we just look at the equivalence relation. If there were 2 points in xi minus 1 which mapped to x, then I'd have to have a pair here which had the property that both of them were in xi minus 1. And that's not the case. Right, I mean, unless they're equal. So. Right, so let's call that guy x0. Then, well, there's multiple alphas, so there's multiple instances of this kind of picture. But for each picture, I can look at the restriction of f to that circle, which is what I'm drawing there. Perhaps I'll call that f alpha. So f alpha just means f restricted to the alpha, the copy of the circle indexed by alpha. And then the pre-image of that point under f alpha, well, it could be empty because maybe one of the other attaching circles, so suppose this is another circle, maybe f maps that somewhere else, right? In which case, so this is f beta, say. Okay, so the pre-image of x0 under that map is empty. So it could be empty or not, but whatever it is, it's closed because this is continuous and this is a closed point. That's a closed point because that space is Hausdorff. All right, so let's draw pre-image in this way. All right, so this is meant to be then f alpha inverse of x0. Well, so that closed subset of the circle sits inside the disk as a closed subset of the boundary. Now, these points here also belong to the disjoint union, right? Because they lie in the disks. And where do they go under rho? Well, by definition, they're all equivalent to points which are sort of along that attaching circle in xi minus 1. And in particular, so they're all equivalent under that definition to x0 itself. Right? So all of those points are attached to x. Now, it's worth remarking that in the image, because the way I'm drawing it always injective, right? F is an injective map. It maps the circle into xi minus 1, as the picture's suggesting that. But that's not necessarily the case. It could collapse the whole boundary disk, boundary circle into a single point, for instance. Okay, so that's the situation. Okay, so given an open neighborhood U of x0 in xi minus 1, well, so what are we trying to do? We've got some y. We haven't been specific about where that is at the moment. We'll come back to that. So we're just focusing on x for the moment, figuring out how to construct an open neighborhood of x in xi from what we know about xi minus 1 and the disks. So this is just a preliminary sort of construction. So we're focusing on x for the moment. And given an open neighborhood of x0, well, this is a bit tough without my green chalk, but we'll try. So there's there's an open neighborhood of x0 in xi minus 1. The pre-image of that in the boundary circle, at least according to this picture, is sort of that open set that I'm drawing with my finger, right? Which is something like this. Right, so that's f alpha inverse of u, and I have one of those for each alpha. Okay. So what's the point? The point is that the image of that open set, that's U, is not necessarily an open neighborhood of X. Right? Because if it contains, an open neighborhood, so here's sort of the image of U. Well, if X is certainly in the image, but if X is in the image, then there needs to be some little neighborhood of X that's in that set. But if I travel from X out onto that disk that's been attached, sort of sitting at X, looking up at the sort of disk coming in, then I move a little bit vertically, and none of those points are in my open set. So can't possibly be an open neighborhood. Okay, so what we've got to do is we've got to find some neighborhood of that stuff, which we throw in, which will fill out this open neighborhood in the direction of the disk that's attached at X. That's the idea. All right, so that's my notation. U alpha. Well, as I said, this set here in white is f alpha inverse u. That's open. So it's open in the subspace topology on Si minus 1 as a subspace of of the disk. And well, by definition, that means there's an open subset of the disk which restricts to the boundary to give f alpha inverse u. So just pick one. In a minute, we're going to be more choosy about which one we pick, but for the moment, pick anything. So let U alpha be an open subset of the disk, such that when I intersect it with the boundary, I get the guy that I want. Okay, so there's the sort of open set I have, and then just pick an open neighborhood which extends that out to the disk. And that thing there is my choice, U alpha. All right. So let's let U tilde be the original open subset of Xi minus 1, together with, for every alpha, this choice, U alpha. Well, where does that live? Well, it's got points from Xi minus 1, and it's also got points from the disks. So it's an open subset of that disjoint union. All right, so claim U is saturated. With respect to this equivalence relation, which is floating around. Ah, damn. Oh no, okay, it's up there. All right, so what does it mean to say that this is saturated? It means that if I have a point in the disjoint union which is equivalent to a point in U tilde, it's already in U tilde. Okay, so what we've got to do is just stare at the equivalence relation and convince ourselves that that's the case. Okay, maybe I'll take questions. Yeah.
Can you just talk us through the definition of U tilde again? Use that notation.
Sure, yeah. So I presume that the picture maybe is clearer than what's over there, yeah. So U tilde is just that with all of those. Okay, so per alpha, so per disk that's being glued in, I've chosen an open subset. I've chosen it in such a way that it contains the preimage of x0 and meets this chosen, sort of fits with U in the sense that this bit here, which ends up being on the disk there, is exactly the intersection of my chosen U alpha with the boundary of the disk. So that condition, so maybe this condition here maybe is the more mysterious part. So let me draw that in the picture. Okay, so suppose I just took an open subset of the disk. Well, when I glue that in, that's going to look something like this, right? And all that condition says is that part matches with U. Yeah, it's literally what it says. It says U alpha intersect the boundary. That is, I take the open subset of the disk and I intersect it with the boundary. So that's that. The solid line I just drew, that's the intersection of U alpha with the boundary, the left-hand side, should be equal to, well, F alpha inverse U is just another way of saying U intersect with that boundary circle as well. So those two solid lines need to match up. That's all that condition says. So that's why we engineered the U alphas that way. And then I just take U together with all the U alphas. And, well, from the way I've set up this picture, you can see now that these fit together correctly. Yeah. Other questions? Okay. So why is that saturated? Well, look at the condition tilde. Suppose we had a point, I don't know, well, suppose we have a point in the disjoint union. It's either in xi minus 1 or in one of the disks. Let's suppose, first of all, it's in xi minus 1 and that it's equivalent to a point in U tilde. Well, therefore, it must be equivalent. Okay, so if it's in xi minus 1 and not in the image of the circles, well, then it can only be of the first kind in the tilde, so it must be already in U. If it's in the image of one of the circles, then the only way it can be in the equivalence relation is if it's one of the FS's, so it's equivalent to the S, which is one of these points down here, but that's already taken care of by the way that I chose, the way that I set up the U alphas. In particular, by the way I made the intersections equal to F alpha inverse U. Yeah, I think this is not something I can really say in words. One just has to sort of think about that for a minute. Okay, so it's a saturated open subset, and therefore its image is an open subset of Xi. All right, and it's exactly the thing that I just drew. All right, so it's just extended this part. So altogether, this is U tilde, or row of U tilde. And it contains X, so it's an open neighborhood. Of X. All right, so all of that was a way contingent on, well, a family of choices to construct an open neighborhood of X in Xi. What were the choices? Well, I got to choose the open neighborhood of Xi minus 1, and I got to choose the U alphas subject to some constraints. Okay, but there was some freedom in those choices. So now, by just making the choices slightly differently, we'll show that we can do the required, or produce the required neighborhoods of X and Y. Okay. Well, maybe I'll get rid of this. So again, there's two cases, depending on whether Y is in the image of the circles or not. So let's say case 1. So y also lies in the image of the disks, sorry, the circles. Maybe I'll just do this case and leave the other case for you to read, because it's actually easier. Okay, so this is the case where y also, I need a bigger circle, I guess. Okay, so y is here somewhere. All right, well, so I can just run the same sort of construction for y. Okay, so again, let y0 be the unique preimage of y in xi minus 1. Then for each alpha, so y0 is the intersection of rho inverse y with xi minus 1. And then I've got, for each alpha, I can take the preimage of that y0. So that's going to be some other closed subset of the circle. I mean, it doesn't meet x0, right? Because they're distinct points. And all of those guys map to y0, and all of those guys map to x0. Okay, so there's the... All right. So choose an open neighborhood. So now we've got both x, y in the game simultaneously while I'm making these choices, right? But I had some freedom in the choices. So choose open neighborhoods uv of x, y, respectively, such that u does not intersect v. I mean, that I can do because xi minus 1 is Hausdorff. Right? That's the inductive hypothesis. So I can choose, let's get rid of this. I can choose this to be my v. Well, then the preimage. Oh, thank you, yeah. Yep. All right, so then the preimages don't meet either. Okay, so this is f alpha inverse v. Okay, so then what we need to do is choose for each alpha, u alpha and v alpha, open in di alpha, such that, well, they satisfy the conditions. So that is u alpha intersect the boundary is f alpha inverse u, v alpha intersect the boundary is f alpha inverse v. So there's and as the picture is indicating, I want them to also be disjoint. Okay, so and u alpha intersect v alpha is empty. Okay, that you have to think about a little. I'm not saying that's immediate. So it is possible to choose the u alphas and v alphas disjoint in that way. That's almost sort of Hausdorffness, right? Except these aren't points, they're closed subsets, and I'm asking for the intersection, an additional condition that the intersection with the boundary is a prescribed open set. Okay, so this is an additional check. I've left it as an exercise in the notes, but okay, it's true, and just a little bit of work. So, all right, so we've arranged our sets in this way. So that means we get u tilde and v tilde. So U tilde is as above, V tilde is V, together with, for each alpha, this V alpha. And, well, V tilde is saturated by the same reasoning, and the image is therefore an open neighborhood of Y in Xi. Right. So we took V, and then we've extended it out onto the disk. You need to imagine that there may be, 100,000 additional disks glued in, all at the same spot, overlapping in some crazy way. That's why we have to choose for each alpha some disks, but that's all okay. All right, so we've got two open neighborhoods of X and Y. Well, the claim is that the intersection is empty, and then we'll be done, right? Well, to be in the intersection, it'd have to be the image of something. You'd have to have a point whose image was simultaneously in U tilde and V tilde. But the way it's constructed, with these being disjoint and all of these being disjoint, is exactly what you need to see, show that isn't possible. Okay, so by construction, they're also disjoint. So, well, that's it for that case, right? So we've constructed the desired open neighborhoods. And then there's the case where Y is not in the image of the circle, so Y is out here somewhere. But then just choose your V to be something over here which doesn't meet U and doesn't meet these closed subsets either. And that's already enough. So the case 2 is easier. So that's it. So this thing is Hausdorff. Right, so let me pause there for questions. All right.
I guess the argument is that the question mark doesn't introduce any overlap.
That's right, yeah. So the argument...
You kind of know that that's true.
Yeah, so so the picture is 99% convincing.
Yeah.
So to fill in the remaining 1%, which is in fact 100%. So what's the argument? Well, it's, again, just stare at tilde. Right? I mean, tilde tells you precisely what gets identified. So if you want to know if 2 points get identified into the intersection of these two things, then you need to look at tilde, and tilde will tell you it's not possible. Yeah. So what's behind my statement that it's true is just to stare at tilde again. Yeah. Okay. So I mean, the only detail I really left out was this little argument. Any other questions? All right, so I had a good question at the end of last lecture, which was, well, why not just prove that a finite CW complex is metrizable, and then you'll know it's Hausdorff, and you don't need to mess around with quotient maps. That's a reasonable argument. However, unfortunately, the generic theorems that say that a Hausdorff space with additional conditions are metrizable are non-trivial, much more non-trivial than this. You may be able to by hand write down a metric on your CW complex, but that doesn't seem very straightforward either. So, I mean, I'd be very interested if you find an argument by first producing a metric on your CW complex. But standing here right now, it seems like that would be more difficult than this.